Gibbs free energy, when Gibbs free energy is positive, then you're not really, that means you would have to put energy into the system, some outside intervention to make the reaction happen, which would mean that the KEQ, the equilibrium constant, would be a small number, less than 1, and you wouldn't really make any products. This is you sitting outside with your chair not moving it. And so the inverse is true for the other one. When Gibbs free energy is large, and negative, I mean, the absolute value would be large, but when Gibbs free energy is negative, work can be done by the system. That would mean you would do the work as you were making products, so the equilibrium constant would be a large number, larger than 1, and you would make products. So that's that. Now, we did this already, and we had said that we fill this in, all these values. If we have the entropy being negative 100 and the enthalpy being negative 20, the system is going to contain mostly reactants because we had found that the Gibbs free energy was positive. We did this already. Okay, so check this out. I don't think we did this. This is where we stopped. Okay, so for the above reaction, the enthalpy is negative, so that's good. That tells me, okay, probably thermodynamically favorable, at least under some circumstances. But then, of course, the entropy is also negative. So this is one of those situations where I would have to, if it was asking me for qualitative stuff, I could draw little smiley faces and figure it out. Low temperatures, high temperatures, whatever. But in this case, it wants me to find the Gibbs free energy. You can already find the Gibbs free energy. Find the Gibbs free energy. Ready, go. When you're given the enthalpy and the entropy, you want to find Gibbs free energy. This is Gibbs free energy is equal to enthalpy minus temperature times entropy. You know the formula I'm talking about? I didn't say that fast at all. So this is the formula you use over and over and over again in the lab. So your Gibbs free energy that you should have gotten, if you have it in kilojoules, which you should have it in kilojoules because that's the typical unit for Gibbs free energy, that is not enough of a line to do anything with. Should have gotten 142, or excuse me, negative 142 kilojoules. Did you get that? And that's per mole. How you feeling? Did you get that?
Yes.
Yeah, you did your lab. Okay, good. Now, what we're going to do, notice that this is asking me to relate it to KEQ. If you recall, I know it's been like 4 days, but look at your formula sheet. Look at your thermodynamics. What we're going to be using is we're using like the 5th formula down. 1, 2, 3, 4, excuse me, the 6th formula down. Gibbs free energy is equal to negative R times T times the natural log of K. Did I introduce that real quick? All right, now check it out. If you look up at the R under the gas constant, remember where that was found? R is equal to 8.314 joules per mole times degree Kelvin. So, did you see how on this PowerPoint they left it as joules? That's why. When you go to put it into this formula, because your gas constant, which you can't really do anything with, you got to use as a constant, is in joules, you have to leave your, you're going to want your Gibbs free energy to be in joules. Now look at me in the face, don't freak out. I don't have a single memory of ever doing a problem like this for an AP exam question. It could happen, it's on this formula sheet, it's on that thing. So if you're like, ooh, I might forget that, well, use your units and make sure you check yourself. But I'm telling you right now, they're going to ask you those questions about K versus G versus like Q, all that kind of stuff. That's what they're going to be asking you. It's not going to be little piddly equations, you wish, okay? But anyway, if we're going to solve for this, if we want to solve for K, that's what we're trying to get, we're going to take this equation and we're going to go ahead and rearrange it to solve for K. So we have Gibbs free energy is equal to negative R times T times the natural log of K. Now I'm solving for Kp, okay? So what I need to do is I'm going to divide both sides by RT. Just good old algebra here. And that will give me, I don't know if it's going to freak you out. I'm just going to rewrite it with K on this side. Have I lost any children? I just flipped it around and made me feel better about my life. Good so far? Now, if you recall that the inverse operation of taking the natural log is raising it to as a power of E, right? You recall that? So, if I erase this sign, if I make this sign an exponent on E, that takes care of the natural log, and I'm left with K. And then I gotta erase this sign as an exponent. So basically, I'm gonna have to put in my Gibbs free energy divided by R times T, and then in my calculator, I'm gonna say E to that answer. So it's not the worst thing that's ever happened to you.
We need to convert our energy to
Joules. All right, so I'm gonna put this stuff in here for you. This looks a little bit messy, so I'm just gonna rewrite it. I'm gonna rewrite it nice and pretty for you. When you rearrange the formula, you get Kp is equal to E, downside, forgets what I was doing, Gibbs free energy, and it's negative. The formula had a negative sign in it, if you recall, divided by RT. Okay, now let's fill this in, make sure we got it. Now, check it out. Negative, right? 142,000. Was that the answer on the last slide? Joules? Per mole. So that's really positive, man. Divided by 8.314 joules divided by moles times degrees Celsius. And then, did it give me a temperature? 298. Okay. So, 298 degrees Kelvin. This is really a test of can you use your calculator. And let me tell you the fastest thing to do. You want to go in your calculator, and you don't want to, like if you play the game, I'm going to hit E to the parentheses. No, don't do that. Look at me. I screw up stuff all the time. Don't do that. So in your calculator, go 142,000. And it's positive because we worked that out already. Divided by parentheses. 8.314 times 298. Close that parentheses up. Now that is the exponent on the E. So now go hit second and natural log and get that E going. And then answer. And don't close your parentheses on the answer. Let me know when you get 7.78 times 10 to the 24th. Well, whatever. Close enough. So did you get something that looks like this? Yeah?
Yes.
How many times? Did everybody successfully push the buttons in your calculator right? No. Who said no? Alright, so in your calculator, alright, follow along with me. Don't try to do E first. You get that answer and then you use E. Alright, so go 142,000 divided by parentheses 8.314 times 298. Close up the parentheses. Now hit enter. You should have 5.73 times 10 to the first, or basically like 57. Okay. Now hit second and your natural log button, which will give you the E to the. So E to the. Then hit second and get your little answer thing going. Do not close the parentheses because it wouldn't matter if you did anyway. But it'll give some weird thing to do, and you're gonna get 7.78 times 10 to the 24. Did that happen? I don't have, like I said, I don't have a single memory of ever having to do one of these. 0 times. Okay? This would be better. I would like this. It could show up though. You never know. I don't know. Alright, so that's that. If you fill all the stuff in, that's what we just did. Now let's think about what this actually means, y'all. The Gibbs free energy, we found a second ago that the Gibbs free energy was negative 142 kilojoules per mole. That's what we found a minute ago, right? So we would expect the equilibrium constant to be large and positive. It's always positive, but be a lot larger than 1, right? And it is. So you could use your mind. That's the part that you need to understand. I mean, using your calculator is cute, but that's really the main idea. We don't have to do Kc to Kp, so I'm skipping this first part. We're going to use their Kp value. See, their Kp is 36.5. So we're going to use 36.5 as our Kp. All right, let me rewrite this for you. Find Gibbs free energy given that Kp is 36.5. So you would just fill it into the formula the other way. This is actually really easy. I'll take 32 seconds at the beginning of class to work this out for you. And if you want to go and start on your homework, I know you're skipping, I feel like it's like 1, 11, and 16. Skip number 1 and work for a while, and I think it'll be fine. I can look real quick if you want to. If you feel like you're going to do homework tonight, I can look for you. Yes.
You can go get my binder so I can show you.
That would be fine. Thank you. Yeah, it's 111 and 16 ain't even a thing. 111 and 14 you're skipping. 111 and 14. Do you want to tape it?
Yeah.
I'll let you tape it. Hit the lights. I really am finished teaching you. All you got to do is fill in the natural log of 36.5. It was, I mean, we were pretty much done. I will show you that real quick tomorrow, though. So you're skipping 1, 11, and 14.
Just for tonight, or?
Yeah, tomorrow, I may give you maybe like 20 or 30 minutes to work on this, and then we got to go into redox, okay? Your third period friends have already finished this and worked on it. Sorry. This ain't hard. So if I were you, I would spend some time on this tonight. You don't have any homework yet, but I'm about to give you some release exams tomorrow. I've just been waiting on a planning period to copy those off. All right, that's it. Peace out. All right, now what am I doing with this class? Things you shouldn't say out loud. I'm on tape.